Hi, welcome to Wise Guys. This video is another series parallel circuit. Alright, so here we have a series parallel circuit, and when you're given all the resistances, normally what you do is solve all the resistances, and then once you've got that all solved, so you sort of move from the outside towards the voltage. Once you've solved your resistances, then the next thing normally is you solve your total current. So you'd have total resistance, total current, and then you sort of work backwards through the circuit to solve all the different parts. So the first thing we're going to do then is solve for the total resistance. We can see that here we have two resistors in parallel. And once we figure out what that resistance is for this piece, we can see that this piece is in series with that 110 ohms. So let's solve for this piece initially, sort of essentially the resistance between these two resistors. So I'm going to call it resistance parallel, and it's 1 over 215 ohms plus 1 over the 150 ohms. And of course this is the formula that we use to solve for the resistance of resistors in parallel. So we do the denominator first, so 1 divided by 215 plus 1 divided by 150 equals. Now what you've solved is the denominator, so then you go to the x minus 1 button in your calculator. So second function x minus 1 equals. We end up with 88.4 ohms. So here we have 88.4 ohms, and that's the resistance of this piece. So a lot of times it helps to just redraw the circuit. So we can say that what we have here then is our voltage, here's R1, here's R2, and then we have our 110 ohms, and that's in series with the resistance we just solved for, and that was our 88.4 ohms. So resistor 2 is our 60 ohms, and resistor 1 is 40 ohms. So then we can see that the 100, badly written, that's supposed to be a 0. 110 ohms is in series with the 88.4 ohms. And all of this is in parallel with the 60 ohms. So then we have this. Here's our 40 ohms. Here's our 60 ohms. And in parallel here, we have 198.4 ohms. Okay, so 198.4 ohms in parallel with the 60 ohms, so we do that math. So that resistance then, so it's basically the second parallel piece, is 1 over 60 plus 1 over 198.4. So 1 divided by 60 plus 1 divided by 198.4 equals, and then second function x to the minus 1 equals 46.1 ohms. So we end up with 46.1 ohms. Now that is this piece, all right? So in the end, our circuit looks like this. And as I've been working through these videos on circuits, I realized that normally when I'm teaching a class, it takes me an entire board to do this. So it's difficult to put it onto this tiny piece of paper. So we have 50 volts. We just solved this. This piece was 46.1 ohms. And this resistor here is our 40 ohm resistor. Okay? So I'm just going to redraw this on the next page. So what we've come down to is this. Our 50 volt battery, all of the parallel stuff is now the 46.1 ohms, and we still have resistor 1 down here, so R1, which is the 40 ohms. All right, and remembering that the circuit was originally this, but we pulled it all together to get to this point. And with this information, we can solve for some of these pieces, all right? So here we are, we've got this, and we can solve for R total. So R total is these two resistors which are in series, 46.1 ohm plus 40 ohms, which is 86.1 ohm. Okay, so that's R total. Now we can solve for total current. I total is E over R, so we have total voltage, which is 50 volts, divided by our total resistance, which is 86.1 ohm. So 50 divided by 86.1 equals 0.581 amps. So we have 0.581 amps for total current. Okay. Now, it's a good idea to take that information back to this circuit. All right. So we say, all right. So I have my total current, and the total current is running through here. And remembering that this is just a smaller version of what we have here, okay? But with this, at this point, we can solve for some pieces here. We can solve for the voltage across resistor 1. We can also solve for the voltage across this parallel piece, all right? So E1 equals IR, and we have 0.581 amps times resistor 1, which is 40 ohms. So times 40 equals 23.2 volts. So 23.2 volts. All right, now that's E1. Now it helps to take that information. Where's the picture of my circuit? Right here. It helps to take that information back to your circuit, all right? And remembering that this resistor is just this resistor. So we have 23.2 volts across this resistor. Now, we can also solve for the voltage across this resistor. We can either take the 50 and minus this voltage, which is the 23.2, or we could use the current times that resistance. So just let's do that piece. So let's call it E parallel is I times R, So again, we have 0.581 amps times the parallel piece of 46.1 ohms. So 0.581 times 46.1 equals 26.8. So 26.8 volts. And that's for this parallel piece across here. Now the other thing is that the voltage across a circuit, let's go back to our circuit here. So here's our original voltage. The voltage drop from here to here across that battery has to be the same across the entire circuit. So we need to have a 50 volt drop across this entire circuit. Now, this is sort of a shortened version of our entire circuit, but we must have 50 volts then across these two resistors. So we can add these two voltages up and see if they actually do make 50 volts, which they hopefully do. And we add, so let's go with 23.2 plus 26.8 equals, hallelujah, 50 volts. Okay, so that tells us that we're on the right track. Now it helps to take this information back to your circuit. All right. So let's go back to our circuit, and I'm actually going to go to a clean one. So if we know that we have 46.1, what did we say? Oh yes, we have 26.8 volts across here. So if we have 26.8 volts across here, we have to have 26.8 volts across resistor 2. Okay? So, and again, the voltage drop across here has got to equal to 50. So that tells us that E2 equals 26.8 volts. So with that information, we can solve for the current through resistor 2. So I2 equals E2 over R2. So we have 26.8 volts divided by 60 ohms. So I2 equals 26.8 divided by 60, which equals 0.447 amps. So 0.447 amps, which is I2. Okay. All right. So now let's go back. And normally what you're doing, especially when you're first starting this, is drawing and redrawing pictures, because it helps you to figure things out. So reminding ourselves that we got the 46.1 when we put these together. So the voltage drop across here, which we know is this voltage, all right? So the voltage across this here is the 26.8 volts. So it's also the voltage drop across here, which is the 26.8 volts. And that's also the voltage drop across this entire resistance piece, which is from here all the way through here and back to there. So that's the 198.4 ohms. So knowing that the voltage drop across this has to be the voltage drop across here, we can solve for our current. So we know that this is 26.8 volts. So we can solve for the current through this piece, which will give us the current through this resistor, all right? So I'm just going to do that right here. So the current here is the voltage, which is 26.8 volts divided by the 198.4 ohms, right? All right. So 26.8 divided by 198.4 equals, so 0.135 amps. Okay, here we go. So the current is 0.135 amps, and that is I, let's call it I parallel, okay? So the current through here, 0.135 amps. Now, this piece I'm hoping that you can see is this piece here, all right? So going along here is 0.135 amps. It splits through here, and then it comes back through here. So the 0.135 amps. We also solved somewhere back here for that parallel piece. Where did it go? Right, 88.4 ohms. So essentially this parallel piece was 88.4 ohms, all right? But let's just deal with this thing. We know that we have 0.135 amps through there, so then we can solve for the voltage across this resistor, all right? So E3 equals IR, which is 0.135 amps times our 110 ohms. And so E3 is 0.135 times 110, which equals 14. Let's go with 14.9. So 14.9 volts is E3. Yeah, okay, let's do that. E3 equals 14.9 volts. So now we have the voltage across here, and we know that the drop from here to this, so let's call this A and let's call this B. We know that from A to B we have 26.8 volts. If we have 14.9 volts across this resistor, we must have, well, not if we have, we must have 26.8 volts all the way across this piece. So from here down there through this parallel piece and back to here, we have to have 26.8 volts. If we have 14.9 volt drop across here, that means we can take the 26.8, subtract the 14.9 volts, and get the voltage drop from here to here. All right? So then E4 equals E5, which equals 26.8 volts minus 14.9 volts. So 26.8 minus 14.9 equals 11.9 volts. Okay, and that is E4 and E5. Now again, this isn't the only way to solve this circuit. This is just one of the approaches. It's a bit like a puzzle when you're working with series parallel, and if you have two pieces of information, you solve for something, right? So we have E4 and E5. Knowing E4 and E5, we can solve for the current through them both. We've solved for the current through there, we can solve for the current through resistor 4 and resistor 5. So I4 equals E4 over R4, and that is 11.9 volts over 215 ohms. 11.9 divided by 215 equals, well, I've been writing everything down as amps, so I'm going to continue that. So 0.055 amps. So we have 0.055 amps through I4, or is current 4. And last but not least, I5. Again, voltage 5, which is 11.9 volts, divided by resistor 5, which is 150 ohms. 11.9 divided by 150 equals 0.079 amps. So 0.079 amps, which is I5. All right. Okay, so I think we've got everything here. I think we've solved for all the currents. What about 3? Yep. So I3 equals to 0.135 amps. Okay, so I think we solved for everything here, and I think that's it. All right, so I hope you have a good day, and I hope that video was helpful. Take care.